Hi, NA Physics, it's Mr. Neff. Let's talk reflection today. Before we do, what do you do when balloons are hurt? I'll tell you at the end of the video. Hey, if you can remember, we started off the interference video with 4 behaviors of waves. We mostly focused on the interference in the interference video. Today I want to focus on one of the wave behaviors, reflection. And you can see that reflection is whenever a wave hits an interface and it comes back into the first material. An interface is a place where the medium ends or changes. And you're going to see that theme recurring in this video and even in the next one. Important to know that when a wave hits an interface, some of the energy is transmitted through the interface into the next material, and some of the energy is diverted back into the first material. I found this very nice video from our friends at St. Mary's University in Canada. Look what they have here. They have some kind of elastic string with some beads on it. And they've got a way here to change the tension on the left and the right side. I see that the wavelength on the left side is rather small compared to the wavelength on the right side. Notice something, that the frequency is the same on both. Look at this last bead on the right and look at this first bead on the left, and they're vibrating at the same frequency. Let's start that again. And you can say, all right, the frequencies are the same. So if the wavelength is small on the right side, that means the wave speed must be small, because the wave speed is the product of the frequency and the wavelength. And on the left side, the wavelength is long. Look at that long wavelength. And so the wave speed must be bigger. But the main reason that I'm showing the video is, you see how when the wave hits this interface, the place where the medium changes, some of the energy goes forward, and so we've got some wave on the left, but then some of the energy comes back. And if I roll that all the way back to the very start, you can see that happening. You can actually see a standing wave being set up on the right, and that's going to be the focus of the next video. So all that is to say that at an interface, some of the energy is transmitted through and some of the energy is reflected back. Now, I found another nice simulator from our friends at PhET, and they have this pretty nifty thing where it's the same kind of thing, an elastic string with some beads on it. Now, I can take this wrench and I can give it a shake, and you can see I did some work on it, but then there are non-conservative forces at work here too, some negative non-conservative forces, and we're getting this damping. Damping is whenever non-conservative forces take energy away from something that's vibrating. That's a little bit more of an advanced concept than we're going to get into. So I'm just going to roll that down to none. And now if I would give this a shake, you would see that that would just go on and on. Now they gave us the ability to change the kind of interface that we have over here. The interface that it starts with is this clamped end. See, they have a clamp on the last bead in the string, and so that clamp isn't allowing that bead to go anywhere. Notice I made a pulse by working up and then down. And so I made this pulse that went to the right above the equilibrium line. And when the reflected part that comes back is inverted. You always see that happening. Whenever a pulse hits a fixed point, you always see that the reflected wave is inverted. That's in contrast to if I would change this to a loose end. Now you can see on the loose end, the last molecule is this ring now, and it can move up and down as it chooses. And that means that it is going to not invert when it goes back. The wrench, of course, is a fixed end, and so it is inverting each time, but the ring is a free end. Now, at first you might think this next part's silly, but they gave us this ability to put a window there. And now you're not getting any reflection, because reflection is an interface behavior. It only happens whenever the medium ends or changes. I get the impression that this medium is just going, 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 and so I didn't get any reflection. There's no interface there. So to summarize all of that, we're going to say that if you send a wave pulse into a fixed end, the reflected pulse will be inverted. I think the artists did a great job on this one. Do you see how tall they made the amplitude of the incident wave? It looks like they made the the reflected wave a little bit less. Why? Because some of the energy went into the second material. In a case like this, there's no way for that to stay as a wave, the transmitted part to stay as a wave, and so it's just going to get turned into heat. Still, the reflected part can't be as big as what went in, or none of it would have been transmitted forward. Now over here, if I have a free end, on the free end, this is going to be able to just move up and down as it needs to, and so the reflected pulse is not going to be inverted, it's going to be upright. By the way, this is the technology that's used by a bat when it's locating some food. You can see this bat has sent out a pulse of sound, and some of that sound is reflected back off of this insect, and the bat is going to notice that, and knowing how quick the sound travels and knowing how long it took, the bat not only knows that the insect is there, but how far away it is. Incidentally, when we did our motion detectors in class, that's the same technology that those use. Whenever you make this two-dimensional, the reflected wave will always make the same angle as the incident wave. Here we've got a little microphone guy, and he's made a clap of sound, as you can see, and that sound is going to travel over here, strike this wall, and make an angle with the normal. We call that angle with the normal theta I, or the angle of incidence, and then it's going to reflect so that this angle, theta R, or angle of reflection, are going to be the same. That idea is called the law of reflection. You don't really see that in one dimension, but in two dimensions you see it all the time. Here's a simulated laser pointer, and you can see that the laser pointer's wave, some of the energy is reflecting back into the air, where some of the energy is going down into the water. What you see there is the energy that went down into the water actually changed its direction a little bit. That's that fourth wave behavior, refraction. We'll talk more about that in a different video. But all this is to say that the incident angle and the reflection angle, well, they are the same. And what do you do with a hurt balloon? You helium.